All right, so today we're taking a deep dive into something pretty fundamental to well, pretty much all the tech we use.
Yeah, we're going right to the heart of how our gadgets actually work.
Exactly. We're talking semiconductors. It's
Yeah.
like chapter 19 stuff, maybe sounds a bit dry,
A little academic, yeah.
but trust me, there's some seriously cool stuff in here. You sent over some great material on this, actually.
Absolutely.
Our goal today is to break it all down, make it clear, interesting, all that good stuff. So no one has to wade through pages of equations to get the really juicy bits.
Right from the get-go, it's kind of mind-blowing to think that everything from those complex chips in our computers to just a simple light bulb lighting up, it all boils down to how materials behave, at the tiniest level, at the level of atoms.
And semiconductors are the key players here.
Right in the middle of it all. And we're all familiar with the basics, right? You have
Yeah.
conductors, the stuff that electricity flows through easily.
Like copper wires, that kind of thing.
Exactly. And then you have insulators, the stuff that blocks electricity.
Rubber.
Yeah, think of the rubber coating around those copper wires, keeping everything safe.
Makes sense.
And then in between those two, you have semiconductors.
In-betweeners.
And what makes them so special is how their electrons are arranged. Specifically, their valence electrons.
So these are the electrons on the outer shell of an atom, right? The ones that are kind of free to move around.
You got it. They're the ones that are involved in electrical conductivity, you could say.
Okay, so conductors have tons of these free electrons and insulators have none. What about semiconductors?
Semiconductors, like silicon and germanium, they have 4 valence electrons. They're right in that sweet spot.
So not too many, not too few.
Exactly. Now, here's the thing. These atoms don't just float around on their own. They link up with each other in a specific way through something called covalent bonding.
Covalent bonding, isn't that where they share electrons?
Exactly. Think of it like each atom wants to have 8 electrons in its outer shell, kind of like a full set to be stable. But they only have 4 of their own.
So they have to share with their neighbors.
Exactly. They're like, hey, you need one, I need one, let's share. And they form these strong bonds with each other, creating a crystal lattice structure. It's like a very organized, repeating pattern.
And this is happening in silicon, right? The main semiconductor material.
Absolutely. Silicon is a prime example. So in its pure form, all the valence electrons are tied up in these bonds, these handshakes between atoms.
So they're not really free to move around and carry a current.
Right. That's why pure silicon by itself isn't a great conductor. It's more like an insulator, actually, in its pure form.
Okay, so it's not a conductor, not really an insulator either. So how do we get it to do something useful in electronics? How do we make it conduct when we need it to?
This is where things get really interesting. This is where we introduce the magic of doping.
Doping. Okay, sounds kind of intense.
It's not as crazy as it sounds, I promise. It's basically a very controlled way of adding tiny amounts of impurities into the pure silicon crystal.
Impurities. So we're messing with the perfect structure.
Exactly, but in a very precise way. These impurities have a different number of valence electrons than silicon.
So either more or less than 4.
You got it. And that tiny difference, adding or removing just 1 electron, completely changes how the material conducts electricity.
Wow, so a tiny change can have a huge impact.
Absolutely. And there are 2 main types of doping, N-type and P-type.
Okay, let's start with N-type. What makes it N?
N stands for negative. In N-type doping, we add an impurity that has more than 4 valence electrons.
Okay, like what?
A good example is arsenic. It has 5 valence electrons.
So when arsenic gets added to the silicon crystal.
It fits in pretty well, actually. It forms 4 bonds with its silicon neighbors, just like silicon would.
Using up 4 of its electrons.
But then there's that 5th electron, the odd one out. It's not really needed for bonding, so it's kind of just hanging out there, loosely attached.
Free to roam around.
Exactly. It doesn't take much energy at all for that extra electron to break free and become a charge carrier, ready to move and create an electrical current.
So by adding arsenic, we're giving the silicon extra electrons, making it easier for electricity to flow.
Exactly. And because these materials now have an excess of these negative charge carriers, these extra electrons, we call them N-type.
Got it. N for negative. Makes sense. So what about P-type? I'm guessing it's the opposite.
You're on the right track.
Oh.
P-type doping involves adding impurities with fewer than 4 valence electrons.
So they're missing an electron to make those nice, neat bonds.
Precisely. A common example here is indium, which only has 3 valence electrons.
So when it tries to fit in with the silicon.
It can only form 3 bonds, leaving 1 spot empty. And this missing electron, this empty spot, we call it a hole.
A hole. So is that like a positive particle floating around?
Not exactly a particle in the same way as, say, a proton, but it acts like a positive charge carrier.
Okay, I'm intrigued. How does a hole act like a charge carrier?
Imagine a crowded room with one empty seat. If someone moves into that empty seat,
The empty seat has moved.
exactly, the same thing happens with these holes. An electron from a nearby silicon atom can jump into that hole, filling it.
But then it leaves a hole where it was before.
Exactly. So effectively, the hole has moved. And this movement of holes, these empty spaces waiting to be filled by an electron, we can think of it as a flow of positive charge.
Okay, so it's not really positive charges moving, it's the absence of electrons, the holes moving around.
Exactly. And because we have these positive charge carriers, we call these materials p-type.
Got it. N-type has extra electrons. P-type has these holes where electrons are missing. So doping is really the key to making semiconductors useful.
Absolutely. It's like taking that pure silicon, which is kind of just sitting there, and giving it a little nudge in one direction or another, making it much more conductive.
So this is all from Chapter 19, right?
Right.
Semiconductor fundamentals.
Right.
And you mentioned earlier that understanding N-type and P-type materials is super important for understanding other components. Can you give us an example? How does this all connect to something we might actually recognize?
Absolutely. Think of a diode. It's a fundamental component that lets current flow in only one direction, like a one-way street for electricity.
I've definitely heard of diodes.
And guess what? A diode is basically just a piece of N-type material joined with a piece of P-type material.
So we're putting those extra electrons in those holes together.
Exactly. And at that junction where they meet, some really interesting things happen because of the difference in charge carriers.
And that's what gives the diode its one-way property.
Exactly. Understanding N-type and P-type materials is like the first step to understanding how diodes and even more complex things like transistors and integrated circuits are built and how they work.
So it's all about manipulating these tiny impurities, these dopants.
It's kind of amazing when you think about it. It's like taking a simple ingredient and tweaking it slightly to create a whole range of different flavors.
Yeah, like adding a pinch of salt or a spoonful of sugar makes a huge difference.
Precisely. And as you delve deeper into semiconductor fundamentals, as Chapter 19 probably does, you'll see that it's not just about adding any impurity. The type of dopant, whether it's phosphorus, antimony, boron, all these different options, they all create slightly different effects.
So it's incredibly precise.
Exactly. And then the amount of dopant you add also matters. You can really fine-tune the electrical properties of the semiconductor material by carefully controlling how much of each impurity you add.
This is like a delicate recipe, getting everything just right.
Absolutely. And that level of control is what allows engineers to create those incredibly complex and sophisticated chips that power all our devices.
It's pretty mind-blowing to think that our entire digital world, all of our computers, smartphones, everything, it all relies on manipulating these tiny impurities in materials.
It's pretty remarkable.
Okay, so just to recap, to make sure I've got all the key takeaways from our deep dive into Chapter 19 here. We started with semiconductors, these materials with their 4 valence electrons, like silicon and germanium. In their pure form, they're not great conductors because those electrons are all tied up in covalent bonds.
Right, those handshakes between atoms.
Exactly. Then we talked about doping, adding impurities to change how they conduct. N-type doping adds extra electrons, making it easier for current to flow. P-type doping creates those holes, which act like positive charge carriers.
And it's the interplay of these two, N-type and P-type materials, that forms the foundation of almost all semiconductor devices, from simple diodes to the most complex microchips.
It's like we've learned the alphabet of electronics.
A great analogy. Once you understand these fundamentals, you can start to decipher how all these amazing technologies work.
So here's a thought to leave our listeners with. You mentioned that the type of dopant and the amount you add can really fine-tune the semiconductor's properties. I'm curious, how exactly does that level of control work? How do engineers decide which dopant to use and how much of it to add to get the exact electrical behavior they need for a specific device? It's like, are there specific recipes they follow?
That's a fantastic question, and it really highlights the incredible depth and complexity of semiconductor engineering. It's not just about making something conductive or not. It's about creating materials with very specific and predictable responses to electrical signals. So thinking about how those choices are made, how engineers manipulate those tiny atoms to create such a vast range of electronic possibilities, that's something to ponder.
It's incredible to think about the level of precision involved in designing these components that power our world.
It really is.
Well, this has been a fantastic deep dive into the fundamentals of semiconductors, thanks to the insights from Chapter 19. Thanks for joining us today, everyone.
Thanks for listening, and keep exploring these fascinating ideas. There's always more to discover about the world of electronics.